In order to multiply radical expressions together, the two radical expressions must have the same root index. Otherwise, we will be unable to multiply them together at this point in time. There is something else we will be able to do later on, but for right now, unless two radicals have the same root index, you will not multiply them together. Now, multiplying radicals together is going to work similar to exponents because radicals are the inverse operations of exponents. So in this first problem, I'd like to try multiplying some radicals. So let's start with the square root of 5 times the square root of 7. Since they both have the same root index, they're both square roots, I'm able to simplify them by multiplying them together. And 5 times 7 is 35. How about the cubed root of 6 times the square root of 2? Those I am unable to multiply because the indexes are different. So we just say that it's already simplified. That's as much as we can do with it. And then the cubed root of -4 times the cubed root of 2. Well, they both have a cubed root, so when I multiply them together, it must give me the cubed root of -8. And it actually turns out that the cubed root of -8, if you plug it into your calculator, is -2. And the reason is because -2 times -2 times -2 is -8. Now we have to stop and talk about this idea of negatives under the radicals. Because there is a case where you will not be able to do what we just did in this previous problem. So I want you to think about this particular problem. For example, let's say I gave you the square root of -2 times the square root of -5. You might think the answer is going to be the square root of 10 because they're both square roots and I can just multiply them together. -2 times -5 is 10. But I claim to you that is not true. The reason is because when we talked about negatives under square roots, we said that the solutions were actually imaginary. And so you would first have to take the I out of the square root. This is going to be true of any even root of a negative number. Then after you take the i's out, you can multiply them together. But we also learned that I squared was equivalent to -1. So it turns out that the square root of -2 times the square root of -5 is actually -1 times the square root of 10, which is not the same as positive square root of 10. So be careful when you're looking at negative numbers under radicals. If the root index is odd, then you can take the radical or you can multiply the radicals. But if the root index is even and you have a negative underneath, those are imaginary numbers, and in this particular unit, we're not dealing with imaginary numbers. Now let's talk about simplifying radicals. This is something that we did in Algebra 1, but it's probably been a while since we've done it. In order to simplify radicals, I'm going to show you two different methods. One method is to determine all the pairs of numbers that multiply together to give you the radicand. And then you pick the pair whose largest perfect square, that has the largest perfect square, I should say. Now, what were perfect squares? Perfect squares were numbers like 1, 4, 9, 16, 25, any number times itself. So if I look at those four pairs of numbers, the one with the largest perfect square is 4 and 6, because only 1 and 4 are perfect squares. None of the rest of the factors are. So I would rewrite that as the square root of 4 times 6, which is the same thing as the square root of 4 times the square root of 6, which is 2 times the square root of 6. The book does this in a slightly different fashion. I prefer this method. The other way of doing it is to create a factor tree using prime factorization. So if I break down 24 into all prime numbers, I find out that it's 2 times 2 times 2 times 3. A square root says, how many groups of 2 of the same thing can I circle? Well, since square root means 2, and there are 2 2's here, I can circle one group of 2's. But then there's no more groups of 2 of the same thing to circle, so I'm left with the square root of 2 times 3, which is 6. We're going to do something similar in order to determine cube roots. Instead of looking for a pair of numbers with the biggest perfect square, we're going to look for a pair of numbers with the biggest perfect cube. What are perfect cubes? 1, 8, 27, 64, 125. Those are all numbers times itself 3 times. So 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3. So now if I go back and I look at all these pairs of numbers up here, that's a very bad looking arrow. There we go. The pair with the largest perfect cube is this. So we're going to rewrite the cube root of 24 as the cube root of 8 times 3. And then I'm going to take the cube root of 8 and the cube root of 3. Well, I can only take the cube root of 8. So the answer must be 2 times the cube root of 3. Now, one of the biggest mistakes students tend to make is they simplify the problem correctly, and then instead of using the correct radical at the end of the problem, they revert back to the square root because they're more comfortable with it. Please watch out for that. Don't revert to the square root. Okay, now I'm going to go and I'm going to do this the other way, which is using the prime factorization. We had already determined that 24 was 2 times 2 times 2 times 3. A cubed root says find a group of 3 of the same item. Well, I only circled one group of 2's, so I take that 2 out, but I couldn't do anything with the 3. Either of these methods work when you're simplifying radicals, and I can use the same process when there's variables under the radical as well. So let's look at this example or problem. We want to find the simplest form of the cube root of 54x to the 5th. Doesn't matter which way you want to do it. So either way you want to go about doing this. If you want to find all the pairs of numbers that multiply together to give you 54, or if you want to do your prime factorization. If you want to find the pairs of numbers that multiply to give you 54, and you want to find out which one has the largest perfect cube, well, think back to the previous page. Look at the perfect cubes here. 1, 8, 27, 64, 125. Oops, wrong direction, sorry. Here's your pair with the largest perfect cube. So we're going to have the cube root of 27 times 2, which is 3, the cubed root of 2, because 27, the cube root of it is 3. Can't take the cube root of 2. To deal with the x's, I write out x 5 times. And to do the cube root of it, I want to find out how many groups of 3 of the same item I can circle. Well, you can only circle one group of x's. And there's still 2 x's left underneath. So if you multiply these back together, you get 3x, the cubed root of 2x squared. If you do it the other way, I'm going to write 2 times 3 times 3 times 3 and then 5 x's. I can circle a group of 3 3's, and I can circle a group of 3 x's, so I can take out a 3 and an x. But under the cubed root, I still have a 2 and 2 x's left over. So either way, I'll get to the same answer. Now let's combine all these properties. Let's talk about multiplying and simplifying. So when we want to multiply two radicals together, remember that the root indexes need to be the same, and they are. So now I can multiply these together. I can multiply the the radicands together. When I do that, I'm going to do 12 times 15, which is 180. X to the fourth times x squared is x to the sixth, because that's the property where you add the exponents. And y squared times y to the third is y to the fifth. Okay, since we're doing square roots, you can do factor tree, or you can find all the pairs of numbers that multiply to give you 180 and which one has the largest perfect square. I'm going to do factor tree here. Since 180 is even, I like to start with 2. So 2 times 90. 2 times 45. Well, now all of a sudden I hit something that's not even. So 45 is 5 times 9, and 9 is 3 times 3. So my prime factorization is 2 times 2. I'm going to write it in numerical order. Then there were 2 3s and a 5. There are 6 x's and 5 y's. So now I'm going to go circle groups of 2 because it's a square root. Those are all my groups of 2. I can take out a 2, I can take out a 3, I can take out 3 x's and 2 groups of y's. But under my radical, I did not circle a 5 or a y. I do have to multiply this all back together, so 2 times 3 is 6, so it's 6x cubed y squared, the square root of 5y. And that is the end of part 1 of multiplying and dividing radical expressions.